Want to feel what it's like to be a forensic investigator, sifting through evidence, connecting the dots.
Sounds intriguing.
Well, today's deep dive takes us right into the heart of forensic chemistry and fire investigations. We've got groundbreaking research from the National Institute of Justice. They're like the authority on forensic science here in the U.S.
The NIJ. Always doing fascinating work. What did you find?
Get this, we're going to see how it all links to a real-life unidentified person case. But first, this online event from the NIJ, Emerging Forensic Science Research. Forensic chemistry caught my eye.
I'm all ears. What jumped out at you?
Okay, imagine this. A crime scene, bustling with activity, and investigators pull out paper sensors.
Paper sensors?
Yeah, they're developing these paper-based sensors to detect even the smallest traces of explosive. Game changer, right?
Absolutely. That's huge for on-site investigations. Instead of waiting for lab results, getting almost instant confirmation about explosives, that could speed things up drastically.
Like something straight out of sci-fi, but it's real. And speaking of futuristic, there's this thing called GC-VUV spectroscopy.
Now that one's a mouthful, even for me. But trust me, it's fascinating stuff. Imagine pinpoint accuracy in identifying substances, even from tiny old samples, like, say, identifying a poison from a decades-old case, just from a hair. That's GC-VUV spectroscopy.
That's incredible. It's like every substance has its own unique fingerprint.
Precisely. It combines gas chromatography, which separates the sample's components, with vacuum ultraviolet spectroscopy, analyzing how they absorb light. So you get this unique fingerprint for each substance. Super precise identification.
So it's like giving investigators a super-powered magnifying glass.
Exactly. And it's not just for poisons, drugs, unknown chemicals at a crime scene. The possibilities are endless.
Speaking of evidence, this NIJ event also highlighted Raman spectroscopy for things like blood or saliva. Must be incredibly helpful, especially with identification.
Absolutely. Think of it this way. Every substance, even body fluids, interacts with light in a unique way. Raman spectroscopy uses a laser to analyze how light scatters off a sample again, a distinct fingerprint. It's like a microscopic eye revealing hidden details.
So in cases where traditional DNA analysis might be difficult, this technique could be key to figuring out someone's identity.
Exactly. Let's say you have a case with a degraded bloodstain. Raman spectroscopy could potentially tell us vital information, like blood type, or even if it belonged to a man or a woman.
This is all mind-blowing. Forensic science is constantly evolving. But before we get too lost in the high-tech world, I want to shift gears a bit. Let's talk fire.
Fire investigation is fascinating. Understanding how fires start, how they spread, their behavior, it's crucial, especially when you're trying to determine if a fire was an accident or deliberate.
Which is where this other NIJ article comes in. How things burn, developing realistic models of how materials combust and degrade in a fire. Scientists are literally building fire models on computers.
And they're incredibly realistic, too. These models factor in everything the materials present, the building layout, even environmental conditions like wind speed.
So investigators can essentially recreate a fire scene virtually and study how it all happened.
Exactly. They can test different scenarios, pinpoint where the fire might have started, how materials contributed to the blaze, even if an accelerant was used. It helps determine if the fire's behavior points to an accident or arson. And that's where it gets really interesting. Remember that unidentified person case? The name use one? It involves a fire.
Okay, it's all coming together now. We were talking about all these incredible forensic techniques, and now we have a real mystery, a fire, and an unidentified person.
Exactly. NAM use case UP6853 all the way back in 1966 in Honolulu. A man found in a burned house. Remains were badly burned, made identification really difficult.
Back then, investigators wouldn't have had access to these tools we've been discussing. Can you imagine trying to solve this case with limited technology?
It really puts into perspective how far we've come. They would have relied on what they could see, maybe some basic lab tests. Imagine trying to figure out what caused that fire without those sophisticated models we have today.
Gives me chills thinking about all the cases out there that could be revisited with this new technology. But let's get back to our case in Honolulu. What do we know about the fire?
Details are scant, which is common in older investigations. We know it was a house fire, but the exact cause, it's a mystery. Accident. Arson. Big questions back then.
Like a puzzle with missing pieces. But this is where our deep dive comes in handy. We've talked about these cutting-edge tools. Could they hold the key to cracking this case wide open?
It's possible. Imagine if investigators could go back to that fire in '66, but with today's knowledge. They could use those fire models, recreate the scene.
Input the house details, the materials, even the weather from that day. Run simulations.
Exactly, like hitting rewind, watching how it spread, pinpointing the origin. We could see things that were missed before or were obscured by the fire itself. Did it start somewhere suspicious? Anything unusual about how it behaved?
Okay, so the models could be huge for understanding the fire itself. But what about the unidentified man? A fire like that, it must have destroyed a lot of evidence.
That's where those chemical analysis techniques come in. Even with limited remains, we might get lucky. Imagine using GC-VUV spectroscopy, that technique that's so precise with identification, to analyze trace materials found with the remains.
Like what? What kind of trace materials are we talking about?
Even after a fire, there might be clothing fibers, environmental contaminants that are unique to a certain place, maybe even traces of stuff he was exposed to while he was alive.
So these tiny pieces become clues to who this man was.
Yes. Maybe they find traces of industrial chemicals he worked in a particular field, or maybe there are residues of plants or minerals from a certain region, hinting at where he might have lived or traveled.
And with Raman spectroscopy, even a little bit of bodily fluid could tell us so much.
Imagine, even with the damage, they find a bit of saliva, maybe on a piece of clothing. Raman spectroscopy could help figure out blood type, maybe even sex. More pieces to the puzzle.
It's incredible how something so small, seemingly insignificant, can be so important with the right tools.
It's the beauty of forensic science. It's always evolving, pushing the boundaries to find the truth, especially in tough cases like this one.
Like solving a giant jigsaw puzzle. Each scientific breakthrough brings us closer to the complete picture. It's one thing to talk about these forensic techniques, but to think about them actually being used in a real case like this, a case that's been unsolved for decades.
It really shows you how powerful forensic science can be, not just for solving crimes, but for maybe even bringing some peace to families who've been searching for answers.
Makes you think about all those other cold cases, ones that seemed hopeless before. Maybe they have a chance now with these new techniques.
That's what I love about this field. It never sits still. It's always pushing the boundaries. Who knows what incredible discoveries are still out there?
Every new discovery opens up a whole new world of possibilities, not just for investigators, but for understanding the past, and maybe even finding some justice. Well, that about wraps up our deep dive for today.
Until next time.
A huge thanks to our listeners for exploring the world of forensic science with us. We'll be back soon with another deep dive into a captivating topic. Until then, stay curious.